Hi everyone, welcome back to Math 256. This is Scott. Let's get started. We are now in the final piece of the Math 256 course. So Chapter 7 is the last of the chapters that we'll be covering, and it starts with 7.1, where we will be introduced to the last big new topic that we will be covering. So this is the Laplace transform. And the inverse Laplace transform. So this section we will be getting first the basics of how the Laplace transform works, and we'll explain in more detail how to actually apply it in later sections. But first, just so that you know what we are going after here, here's the idea. So the Laplace transform turns a function of t into an algebraic expression in a different letter, typically S. So the way we will write it is, so we write the Laplace transform like that, and then it uses a brace, kind of like the set brace, rather than parentheses. And so this will be, and we'll write f of S. So this here represents the Laplace transform of f, not just the antiderivative. So the capital letter can represent several different things. In this case, what we're going to be using a capital letter for is the Laplace transform of a function f. So this is the Laplace transform of f, not the antiderivative. And the purpose of this this operation is that it will have a special relationship with derivatives that will turn differential equations into algebraic equations. So as we'll see later, the Laplace transform turns differentiation into an algebraic operation. And that's the point of it. So then what we'll do, so how we'll use this, we'll take an ordinary differential equation, and then by means of the Laplace transform, that will turn it into an algebraic equation. And then, by means of algebra, we will solve to get the solution. In S, and then we'll do the inverse Laplace transformation to get the solution in T. So we'll do change the differential equation into an algebraic equation. We'll solve that, and then we'll change it back into the original variable. So that's how the Laplace transform will actually get used. Now, here's the official definition of it. See the official definition. So the setup here, we're going to have f of t is a function, and it has to be defined for all t greater than or equal to 0. And then the Laplace transform of f of t is equal to the integral from 0 to infinity. And what we have is e to the negative st, so s is a new variable that's being introduced here, and then times f of t dt. So doing this integration will actually take t completely out of it, and then all that will be left is something involving an s. So our first goal number 1, is going to be to make a catalog of the Laplace transforms of basic functions. So that's going to be our first goal. Now, since this is an operation that is defined by means of an integral, it shares certain useful properties that integrals have, and one tool here is going to be what is called the linearity of the Laplace transform. So, linearity. So note that if I were to take the integral from 0 to infinity of e to the negative st, and I were to plug in, and I were to put in here instead of just f of t, if I were to put a times f of t plus b times g of t, and we're to take that integral with respect to t, this breaks up into the two integrals, and in fact it breaks up a lot, and out can come the a. This is the integral, a times integral from 0 to infinity of e to the negative st f of t dt plus b times the integral from 0 to infinity of e to the negative st g of t dt, which then means, so thus, the Laplace transform of a f of t plus b g of t is actually in fact going to be the Laplace transform of f times a plus the Laplace transform of g times b. So it's going to be equal to a times the Laplace transform of f of t plus b times the Laplace transform of g of t. And this should just have been an ordinary script L. Script L is the usual notation used here. So in other words, a times f of s plus b times g of s. So if we are able to figure out the Laplace transforms of certain basic kinds of functions, we can combine them by linear means. So we can distribute the Laplace transform over addition, and we can pull out a constant factor. Just like we can with differentiation or with integration or with many other operations. Okay, so now let's begin our conquest of functions. So now let's take, so let's make our catalog of Laplace transforms. So let's start with something very easy. F of t is just constantly equal to 1. So we'll start with the easiest category of functions, constant functions. Well then, f of s would be the integral from 0 to infinity, and this is going to be e to the negative st times 1 dt. But we are we're anti-differentiating this with respect to t, so as far as that is concerned, s is just a constant, and so what this is going to be is the improper integral from 0 to infinity. I should rewrite that. What I mean is, it's going to be negative 1 over s, e to the negative st, and this is going to be evaluated at 0 and infinity. Now on this side, this goes to 0 if we plug in infinity, so this is going to be negative 1 over s times 0 minus e to the negative s. And so what we're going to end up with, e to the 0. So what we're going to end up with is going to be just negative 1 over s times negative 1, or in other words, just 1 over s. So the Laplace transform of just a constant is equal to just 1 over s. And this is specifically where s is greater than 0. Otherwise, this one is no longer true. And the reason for this is because e to the negative st will go to 0 as t goes to infinity if s is greater than 0. So in other words, if it has a negative exponent, then it has a horizontal asymptote at 0, which it'll approach as t goes to infinity. So that's the reason for this part right here. However, it's not really going to be our business to be plugging values for s very often into this, so that's just kind of a technicality, actually. Now let's work our way up a little bit, up the ladder. So the next level up from this is going to be f of t is equal to just t. So we went from a degree 0 polynomial to a degree 1 polynomial. And so what we're going to have here is the integral, so f of s is equal to the integral from 0 to infinity, e to the negative st times t dt, which is going to be a case of integration by parts where we're going to have u equals t, making du equal to dt. dv would have to be the e to the negative st dt, which then would make a v of negative 1 over s e to the negative st. And so when we integrate this by parts, we're going to have negative t over s e to the negative st, and then minus the integral from 0 to infinity. Oh, and this is going to be evaluated at 0, infinity. And then minus the integral from 0 to infinity of v du, so it's going to be negative 1 over s e to the negative st dt. So then, over here, what we're going to have is we're going to be plugging in t of infinity, and this will be going to, and this, if s is greater than 0, then t e to the negative st will go to 0 as t goes to infinity, and that's because it's exponential decay versus just linear growth. So exponential beats linear. So this, so remember in 252 when you looked at some of these indefinite, or sorry, these improper integrals, you ended up with that sort of thing. Okay, so that's going to be negative 0 minus, and it's going to be the negative in front of all of it, minus, and then we plug in a 0 for t, and it's going to be a 0 as well. And then over here we're going to have now plus, and then out is going to come the 1 over s, and then it's going to be times negative 1 over s again, and then times e to the negative st, and it's going to be evaluated again 0 at in infinity. And if s is greater than 0, then this part is going to be going to 0, and this part will be fixed at 1. So this is going to be equal to negative 1 over s squared, and then what we're talking about here is going to be a 0. I pulled out the negative, so it's going to be minus, and then 1 over s, I pulled that out, so then it's just going to be minus 1, which is going to be equal to 1 over s squared. Okay, so far we've got the integral, or the Laplace transform of constants and of linear down. So then, as an example, let's say I wanted the Laplace transform of 3t plus 2. Well then, here it would be just 3 times 1 over s squared, which is the Laplace transform of t, plus 2 times 1 over s, which would be the Laplace transform of the constant term. And here then, 3 over s squared plus 2 over s. It'd be customary here to get a common denominator for reasons you'll see later. And so that's going to be 3 plus 2s over s squared as the Laplace transform of that sum. Okay, now if we were to continue the process of doing these integration by parts, then what's going to be happening is that we are going to end up with more and more links in our differentiation by parts chain, And we can skip to the more general case. So in general, or in almost general, if n is a non-negative integer, then the Laplace transform of t to the n is going to equal n factorial over s to the n plus 1. And you can just you can prove this if you want inductively just by iterating the number of integration by parts that we produce. So for example, let's say we wanted the Laplace transform of 2t to the third. Well, that would equal 2 times 3 factorial over s to the 3 plus 1. So that's going to be 2 times 3 factorial is 3 times 2 times 1. It's going to equal just 6 over s to the fourth. So that'll be 12 over s to the fourth. And in case you haven't seen this before, this is n factorial. It's equal to n times n minus 1 times n minus 2 on down until you just get to a 1. Oh, and specifically, in case you haven't ever seen it, special case, 0 factorial equals 1. To learn more, Google factorial. So 3 factorial is 3 times 2 times 1, which equals 6. Okay. Now, if n is not a non-negative integer, now, if n is not a non-negative integer, we can use the gamma function as a generalization of factorials. So here's a rundown on the gamma function. So gamma function. First off, the definition. So the definition of the gamma function is that the gamma of x is equal to the integral from 0 to infinity of e to the negative t times t to the x minus 1 dt. So it's defined in a way that's kind of similar to the definition of the Laplace transform, but the reason why it's defined this way is that this kind of an integral has a certain property, and when you go around integrating this, you end up using integration by parts, and then by integrating by parts, we would learn, I'll leave the details to you if you are interested in integrating by parts. We would learn that the gamma of x plus 1 is actually the same thing as x times the gamma of x. And furthermore, if we actually wanted to integrate, if we wanted to evaluate this on down, we would get that gamma of 1 was equal to 1. And so what that means is that actually if we were to go up the ladder, then we could see something like this. So an alternative way of looking at this is that gamma of x equals x minus 1 times gamma x minus 1, which means that we can build up to the next level by multiplying by whatever level we're at, and this leads us to, so also we know that gamma, or we can find that gamma of 1 equals 1. Together, these would lead to gamma of x plus 1 is equal to x times gamma x, which will be x times, then we just basically repeat the process moving down one step, x minus 1 gamma x minus 1, and so on, dot dot dot, until we get x down to minus 1, x minus 2, dot dot dot, down to 1, and this is if x is a positive integer. Which would mean that gamma of x plus 1 corresponds with x factorial. Which will then lead us to the conclusion that the Laplace transform of t to the a would equal, it would be a factorial if it could be, but if it can't be, then it'll be gamma a plus 1, in the case that a is not an integer or not a positive integer, divided by, and then s to the a plus 1. Now this is easy to write down, but it's not easy to evaluate unless we know some more properties about gamma. So to actually evaluate gamma of a plus 1, it helps to have some useful facts. Alright, and in particular, the one main useful fact that we are going to be using is this. So this one is going to seem like a real shot from the blue here, but it happens to be the case that gamma of 1/2 is equal to the square root of pi. Now, if you want to know why that is, it comes down to a certain amazing fact. So this comes from a certain amazing fact, and we won't go through the details of how it comes from this, but it is interesting, and I don't want you to go your whole lives never having seen this. But the integral from negative infinity to infinity of e to the negative x squared dx is equal to the square root of pi. So it's an amazing fact, it happens to be true, it's useful in statistics, and it is related to this. I'll let you work out the details, or try to work out the details, and then if you run into trouble, we can always go over it with somebody at some point. If you ever desire, just get in touch with me, be happy to discuss the details of that. Now, using this, let's say I wanted to find gamma of 3/2. Well, that's equal to gamma of 1/2 plus 1, which, as we just saw, is the same as 1/2 gamma 1/2. So gamma function has this very weird kind of recursive property where the number here can be pulled out, and then that leads us to 1/2 square root of pi. If I wanted gamma of something like 7/2, that would be the same as gamma of 3/2 plus 1, which would then be, that'd be 5/2 plus 1, which would be 5/2 times gamma of 3/2 plus 1, which would then be 5/2 times 3/2 times gamma of 3/2, which would then be 5/2 times 3/2 times 1/2 root pi. Notice what's happening here is the numerators here are counting down by odd numbers. The denominators are just equaling 2. So then we're going to have 5 times 3 times 1 is 15 over 8 root pi. So then, for example, if I wanted the Laplace transform of let's say t to the 5/2, that would be the same as gamma, and then this power plus 1 would be 7/2 divided by s to the 5/2 plus 1, which is 7/2. And so that'll be 15 over 8 square root of pi over s to the 7/2. Alright, so that's what to do in the case of a power function where it's not an integer power. Now, exponential functions. Let's say f of t is equal to e to the at. So if f of t is equal to e to the at, then, oops, just got in the habit of writing those gammas, so it corrupted my capital F. So f of s would equal the integral from 0 to infinity of of e to the negative st, this is by definition of the Laplace transform, e to the at dt, which would be the integral from 0 to infinity, e to the t times a minus s dt, which then is going to be an integral where we have, these are both constants as far as t is concerned, so it's going to be 1 over a minus s times the integral, times e to the t a minus s evaluated from 0 to infinity. And then if what we have here is an s that is greater than a, so if s is greater than a, then e to the t times a minus s will go to 0 as t goes to infinity. So what that means is this is equal to 1 over a minus s times 0 minus, and then if I plug in 0 for t, this is going to be a 1. And so that's going to be negative 1 over a minus s, which is the same as 1 over s minus a. Okay, we'll be summing these all up in a big table once we're done assembling our catalog. So now we've got exponential functions under wraps. Now the next major category of functions to tackle is exponential functions. Trigonometric functions. However, trig functions are actually related to the exponential function according to Euler's formula. So let's take a look at that. So trig functions. So we'll use again Euler's formula, which those of you who've been around the calculus block and taken Math 253 will have seen, where this, at least one derivation of this, based on the power series for sine, cosine, and e to the x, although this formula actually predates that. It actually was originally derived as a result of some other facts related to the trig functions. But anyway, e to the ix is the same as cosine x plus I sine x. So now, let's say I wanted to do the Laplace transform of e to the I k t. Well, according to what I just found here, that's going to be the same as 1 over, and then a here is equal to ik, is what's going on. So it's going to be equal to 1 over s minus ik. But s minus ik, that as a denominator can be cleared up by doing the equivalent of rationalizing it, which is multiply the top and bottom by the conjugate. So then if you do that, then what you're going to have on the top is going to be s plus ik, and on the bottom, if you FOIL that out, it's going to be s squared minus ik squared. The middle terms will cancel out. But the whole point of I is that when you square it, this becomes negative 1, so then this is going to be s plus ik over s squared plus k squared, which is going to equal s over s squared plus k squared plus I. I'm just reorganizing this, times k over s squared plus k squared. So then separating out the two pieces here, so this is the sine and this is the cosine. And so then, if we collect the real parts and the imaginary parts, so thus, the Laplace transform of cosine of kt will be equal to the s over s squared plus k squared, and the Laplace transform of sine kt will be equal to the k over s squared plus k squared. So there, now we have the sine and the cosine taken care of. And again here, for technical purposes, we will stipulate that the analysis here only worked if the improper integral converged, which only happens if s is greater than 0. But plugging in values for s is not really actually our game here. What this actually is turning it into the algebraic expression in s. So we're not actually interested in which value we're plugging in for s. We're interested in making an algebraic expression for s. Okay. Now, the next pair of functions that we're going to look at are what are called the hyperbolic trig functions. So we have cosh, which is the hyperbolic cosine function, is equal to, and you can write it a bunch of different ways, but I'm going to write it as 1/2 e to the x, cosh x, is equal to 1/2 e to the x plus 1/2 e to the negative x. And sinh is equal to 1/2 e to the x minus 1/2 e to the negative x. So you probably saw this at some point during Calc 1, I think, was when these were first shown to you. So they are the hyperbolic trigonometric functions. It's hyperbolic cosine, hyperbolic sine, pronounced cosh and sinh. Now, then if we want to do the Laplace transform of cosh t, so defining the functions with using x's, and then when it comes time to talk about the Laplace transforms, I'll make it the default variable t and actually make it a kt. So this would be the Laplace, so it would be 1/2 times the Laplace transform of e to the kt plus 1/2 times the Laplace transform of e to the minus kt. Now, if we look at how this is going to play out, it's going to be 1/2 times 1 over, and then here we've got k playing the role of what we usually call an a, so then that's going to be s minus k plus 1/2 1 over s minus negative k. It's going to be s plus k. Now if I want to combine the like terms, I'm going to have to multiply the top and bottom of this by s plus k, and the top and bottom of this by s minus k. So here we go. Also, the 1/2 can be pulled out. So it's going to be s plus k over s minus k, s plus k. I pulled out the 1/2, so then this one's going to be s minus k over s minus k times s plus k. And so then what we're going to have here is 1/2 2s, the k's will cancel, over s squared minus k squared, and those, that doesn't cancel. Sorry, my mistake. What cancels is that. So the 2 and the 2 cancel, so what we've got is s over s squared minus k squared. And here as a note, once again to make things nice and well defined and convergent and all that, I'm going to put in a little disclaimer. We're never going to make use of this, but we're going to announce it. S has to be greater than the absolute value of k to avoid this being negative, and to make sure that the things in question here are always convergent. And then for the sinh, it is basically the exact same thing, but with minus, minus, and that'll change that slightly. So the Laplace transform of sinh kt is going to be 1/2 Laplace transform e to the kt minus 1/2 Laplace transform e to the minus kt. So same thing, 1/2 times, now here we're going to have 1 over s minus k. Here we're going to have minus 1 over s minus negative k, so plus k. And then that's going to be 1/2. So combining like terms, we're going to, finding a common denominator, we're going to have s plus k over s minus k, s plus k, minus s minus k over s plus k, s minus k. And so then that's going to have the effect of canceling now the s's, and it's going to be 2k over s squared minus k squared. Sorry, that's 1/2. 1/2. And so then that's going to give us k over s squared minus k squared. Okay, so that is the hyperbolic sine function. Now, when it comes time to evaluating some other types of functions, it's useful to have on hand, on the tip of our tongue, some useful trig identities that we will need. So these are both a consequence primarily of the cosine addition formula. So sine squared x is equal to 1/2 minus 1/2 cosine 2x, and cosine squared x is equal to 1/2 plus 1/2 cosine 2x. So these, you'll recall, came in handy from time to time in finding an integral, for example. Now, as an example, let's say you wanted to do something like the Laplace transform of cosine squared x. T, I mean, t. Well, that's going to be 1/2 times the Laplace transform of just 1 plus 1/2 times the Laplace transform of cosine 2x, 2t, keep saying that, because it's written up there. Okay, so this we already know, it's 1 over s. Now this one we also already have figured out. This is going to be, so this is have it playing the role of k equals 2. So this is going to be s over s squared minus 4. Sorry, plus 4, I mean. The minus was for cosh. So trig is plus, hyperbolic trig is minus. That's the important thing about that. Okay, so then that's 1/2 1 over s plus s over s squared plus 4. So if I want to get a common denominator here, I need to multiply the top and bottom of this each by s, and I need to multiply the top and bottom of this each by s squared plus 4, s squared plus 4. So then that's going to give us 1/2, and on the top what we're going to have is going to be s squared plus 4 plus s squared. On the bottom, we're going to have just s times s squared plus 4. And so then, simplifying that down a little bit, we're going to have a 1/2. We're going to have 2 s squared plus 4, s squared plus 4. And so this, the 2 will cancel with that, and we'll have s squared plus 2 over s times s squared plus 4. The last category of functions that we will put into the catalog come from the heading of what are called piecewise continuous functions. And what these mean are functions that come in discrete pieces that are each continuous, but maybe overall there are gaps or something like that. So these are functions made of a finite collection of let's say continuous pieces. So an example of this would be what is called the unit step function. Or also called the Heaviside function. So the unit step function or a Heaviside function. So this is by default u of t, which is equal to the piecewise function that is 0 as long as t is less than 0, and then becomes 1 if t is greater than or equal to 0. So then graphically what this would look like is up until 0, the function's graph is just right along the x-axis, and then after that it's like a switch turns on and it becomes defined. and it becomes equal to 1. So there's this, and then there is the shifted version, u sub a of t, which is equal to u of t minus a, which gives just a shift to the right by a units. And this is, this looks like, so this looks like this. So it's just the whole thing shifted over. Now, because the Laplace transform is defined by an integral, we can actually just take the piecewise defined integrals and just do them part by part. We can evaluate the integral that defines the Laplace transform in pieces. So for example, let's say we wanted the Laplace transform of the unit step function u of t, unshifted. Then that'll equal the integral from 0 to infinity of e to the negative st u of t dt. But since the t only turns on, or since the u only turns on at 0 anyway, and the integral only begins at 0, this actually is just the same as the integral from 0 to infinity of e to the negative st dt, which is just 1 over s. This is just the same as the Laplace transform of 1. And here, as usual, s has to be greater than 0. So for the unit step function, because it only takes effect at 0, which is where the integral that defines the Laplace transform, where that integral begins, that is actually not changed at all. It's just the same thing as just the function that's identically equal to 1. Now, if we want to do the Laplace transform of a u shifted, so the Heaviside function shifted to the right by a units, then what we'd be talking about is the integral still 0 to infinity of u sub a of t e to the minus st dt, and it doesn't matter which order I write these in, it's all the same. But this is going to be just equal to 0 to a of just 0 times e to the minus st dt plus the integral from a to infinity of 1 times e to the minus st dt. So we can break up the integral into pieces. And this is just going to equal 0. And this is just going to equal plus the integral from a to infinity of this. So this is going to be negative 1 over s times e to the negative st, plugging in on the one hand a, on the other hand infinity. And so if s is greater than 0, e to the negative st is going to go to 0 as t goes to infinity. And so what that means is we're going to have negative 1 over s, and then here this is going to be 0 minus e to the negative sa, or as. And so that's going to equal e to the as over s, as long as s is greater than 0. Okay. Now, at this point, we can make our grand catalog of the Laplace transforms of various of the important functions that we have just discussed. So here is our table of Laplace transforms. So we'll break it up into f of t on one side, capital F of s on the other, and then next to it we'll put the stipulations on the s. Okay, so first off, what we had was the function that was identically just equal to 1, and then that gave us 1 over s with the stipulation that s had to be greater than 0. And then if we just had t, that gave us 1 over s squared with the stipulation still that s is greater than 0. And then if we had t to the n for n an integer, we'll have n factorial over s to the n plus 1. This is s greater than 0 and n a positive integer. And then if we have something other than a positive integer, then what we use is the gamma function as a substitute for factorial. So gamma a plus 1 over s a plus 1, and this is s greater than 0 still. And then what we had was e to the at. And then this gave us, or I guess, what do we write? Oh yeah, so then this gave us 1 over s minus a, and here we needed s to be greater than a in order for the integral to converge. And then what did we have? We had cosine kt. Let me put some order into the universe here. Okay, so if we had cosine kt, then what we have is s over s squared plus k squared. And then if we have on the other hand, and here specifically we wanted s to be greater than 0. We have sine kt. Then what we're going to have. All right, now let's try an example of one of the piecewise functions. So an example here, find L of f of t for f of t given below. And the f of t that we're going to be talking about here is going to be a piecewise defined function that's going to look like this. So it's going to have 3 pieces. One piece that goes up in a linear fashion, like that, going from 0, 0 to 2, 2. And then the next piece will be going horizontally from 2, 2 to 4, 2. Then let's say the next piece goes down like that and goes from 2, 4 to 5, 0. So So this is going to be a piecewise function in 3 pieces, and it's pretty easy to see what 2 of the pieces are. Then the third one we're going to have to do a little bit of work to get. So if we take the first piece here, that's just going to be t. You can see it's just going up. Goes over 1 for up 1, and then this is going to be 0 less than or equal to t less than or equal to 2. And then this next one is just going to be horizontal, so it's just going to be equal to 2, and that's going to be from 2 less than t to 4. And by the way, it doesn't matter which side of the boundary here you put the less than or equal to. It'll all come out the same in the end. And then for this part, let's figure this out. So if m is -2, and it contains the 0.50, then we could say y equals -2 times t plus b, and solve that for b. So that'll be 0 equals -2 times 5 plus b, which means b is going to equal 10, which means y is going to equal -2t plus 10 for that third installment. So -2t plus 10 would do it. And that's from 4 less than t until t is less than or equal to 5. Alright, then the Laplace transform will be 3 parts. First, the integral from 0 to 2 of t e to the negative st dt. Then the integral from 2 to 4 of 2 e to the negative st dt. And then the integral from 4 to 5 of -2t plus 10 times e to the negative st. So let's go ahead and just break those up into 3 integrals, I1, I2, and I3. So starting with I1, what we've got here is a classic case of integration by parts. So integral from 0 to 2, t e to the minus st dt. So we're going to go with a u of t, which puts a du of dt. dv will be e to the negative st, which makes v negative 1 over s e to the negative st. I'm sorry. The dv includes the dt part. So this is going to be the rules of u and v, and so here we go. I1 is going to equal uv, so it's going to be negative t over s e to the negative st, and that's going to be evaluated 0 to 2, minus the integral negative 1 over s e to the negative st dt from 0 to 2. So here, when we plug in 2 for the t, that's going to be minus 2e to the negative 2s over s. Over here, we're going to bring down another 1 over negative s. So it's going to be negative, negative, negative. So it's going to be a total of minus 1 over s squared e to the negative st. And that's going to be going 0 to 2. So it's going to be negative 2 e to the negative 2s over s minus 1 over s squared. And in here we're going to have e to the negative 2s minus 1. Okay, so let's call that good. Of course, we could simplify. We better simplify it at least a little bit. Negative 2 e to the minus 2s all over s minus e to the negative 2s over s squared minus 1 over s squared. But we won't break our plus, actually, on that last one. But we won't break our backs doing too much simplification here. There's no reason to go too crazy on that. Because we've got 2 more integrals to do, we have to keep our powder dry. So now let's tackle I2, which is a little bit of a cool down lap. It's much easier. So 2 to 4, the integral from 2 to 4 of 2 e to the negative st dt. So now this is just going to be 2 negative 2 over s. So s is not 5s. Unfortunately, s is an awkward letter for this very reason. It's very similar to number 5. And e to the negative st from 2 to 4. And so what we're going to have is minus 2e to the negative 4s over s minus negative, so plus 2e to the negative 2s over s. Alright, now for the hard one. I3, which is going to equal the integral from 4 to 5 of negative 2t plus 10 e to the negative st dt, which we can break up into the integral from 4 to 5 of negative 2t e to the negative st dt plus the integral from 4 to 5 of 10 e to the negative st dt. Here, once again, what we've got is a nice classic integration by parts. I'm going to keep the 2 in there rather than take it out so that I save myself the trouble of distributing it later. So I'm going to make u equal to negative 2t. So then du would be negative 2 dt. dv can equal e to the negative st dt, meaning v is going to equal negative 1 over s e to the negative st dt. And that is going to then lead us to uv. So it's going to be negative, negative, it's going to become positive 2t over s e to the minus st, and that's going to be going 4 to 5, and it's going to be minus the integral negative 1 over s e to the negative st times negative 2 dt. So let's see what's going on here. Negative, 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 and then negative, and we're going to have altogether on this one 4 to 5. So on this one, plus the other one over here, the easy one. So that's going to be 10, negative 10 over s e to the negative st 4 to 5. So over here we're going to have 10 e to the negative 5s over s minus 8 e to the negative 4s over s. Over here, we've got a whole bunch of negatives, a positive, negative, but down will come another negative, so altogether it's going to end up being positive 2 over s squared e to the negative st 4 to 5. And then this next one over here is going to be minus 10 over s times, what are we going to have? We're going to have e to the negative 5s minus e to the negative 4s. Okay, finally things are starting to come together a little bit. So 10 e to the negative 5s over s minus 8 e to the negative 4s over s. Here, when we put in, we're going to have plus 2 e to the negative 5s over s squared minus 2 e to the negative 4s over s squared. And then here, minus 10 e to the negative 5s over s. Notice we've got some canceling happening over here. Plus 10 e to the negative 4s over s. So these ones will cancel each other. These two will be like terms. And as for the other two, they'll fend for themselves. So it's going to become just 2 e to the negative 4s over s. Plus 2 e to the negative 5s over s squared minus 2 e to the negative 4s over s squared. And so then we can put all the pieces together and get f of s is equal to. So now the pieces are, from I1 we had negative 2 e to the negative 2s over s minus e to the negative 2s over s squared plus 1 over s squared. And then from the I2 side of things, we had minus 2 e to the minus 4s over s. We had plus 2 e to the minus 2s over s. Then we had plus 2 e to the minus 4s over s plus 2 e to the minus 5s over s minus 2 minus 2 e to the minus 4s over s squared. Alright, and then looking at some like terms, these cancel each other. Let's see, what else do we have here? We also have those are s's and s squareds. Looks like these are not quite going to cancel each other, although they are going to come close. So altogether here, when all is said and done, what we have is negative e to the minus 2s over s squared plus 1 over s squared minus 2 e to the minus 4s over s plus 2. Oh, sorry, I didn't notice those two did cancel. I thought there was something else that was supposed to cancel there. Okay, so those cancel. Plus 2 e to the negative 5s over s minus 2e to the negative 4s over s squared. Now here we can multiply the top and bottom of this by an s in order to give it a common denominator. And so if we wanted, we could pull out 1 over s squared, and it would be negative e to the minus 2s plus 1 plus 2s e to the minus 5s minus 2e to the minus 4s. So that would be a common way of rewriting it in order to simplify it, give it a common denominator. Now the last little twist on this is the reverse process called the inverse Laplace transform. And the goal here is we are given the one that has the s and we want the one that has the t. So the goal go from fs to little f of t. So find the functions from the table we just made, that most resemble the given expression and multiply by a constant. To make it work. Alright, now as an example, let's just say that we started with something like this. So find the inverse Laplace of the following. So let's say we started with something like 3 over s. Well, if we look at the table of Laplace transforms that we compiled painstakingly, always go with the simplest one. If there's more than one option, now the one that matches this is just the constant function, f of x or f of t equals just 1, but we need to multiply it by 3 so that it will equal 3 here. So the Laplace transform, or the inverse Laplace transform of 3 over s would just equal 3. Now let's up the ante rather significantly. Let's take f of s equals s to the negative 3 halves. Now, as written, this is not in a very convenient format for anything on our table. However, the fact that it's a negative exponent means that we may want to reframe it as 1 over s to the 3 halves. Now, 1 over s's, those are very common expressions that we've seen here. In fact, every one of our expressions has an s somewhere in the denominator. But the one that has a power like this is the one that comes from the t to the a. So recall that the Laplace transform of t to the a is equal to gamma a plus 1 over s to the a plus 1. So we're clearly dealing with this here, with A being 1/2. So here, A equals 1/2. But we'll have to divide by the gamma of A plus 1, which in this case is the gamma of 3/2, which as we figured out was 1/2 root pi, or in other words, root pi over 2. So we have to divide by that. So what that means is the inverse Laplace transform of s to the negative 3/2 is going to equal 2 over root pi times t to the 1/2. And if you wanted to check it, then you would just plug in this into there, and you would get gamma of 3/2, which is root pi over 2, divided by s to the 3/2, and so it would it all check out. Okay, so there's that one. Now for our next example, let's try see where we are given f of s is equal to 1 over s plus 5. So here, the closest one from the table, so bring up the table and look it over. The closest one from the table is clearly right here, e to the at. So Laplace transform of e to the at is equal to 1 over s minus a. And so here we're talking about a equals negative 5. So the inverse Laplace transform of 1 over s plus 5 would be equal to e to the negative 5t. Alright, now what if we have something along the lines of this? So let's say we had d 3s plus 1 over s squared plus 4. Now if we look at our table, the basic elements of the table here do not have complicated numerators. So we're going to want to break this up into 3s over s squared plus 4 plus 1 over s squared plus 4. Now this one right here is closest to cosine. This one right here is closest to sine. So let's remember what the Laplace transform of cosine kt is. So cosine is going to be it's going to be s over s squared plus k squared. And so here, s is going to equal 2, k is going to equal 2. S is just s. So here k equals 2. So here k equals 2, and we multiply by 3. Over here we have something that resembles the sine, but that has a factor of k on the top instead of just a 1. So what that means is we're still going to have k equals 2, and we're going to have to multiply by 1/2. So put these two things together, and we're going to get the inverse Laplace transform of 3s plus 1 over s squared plus 4 is going to equal 3 cosine 2t plus 1/2 sine 2t. Now our antennas are going up on this because this has very much the appearance of the kinds of things that we've been getting as results of the various calculations we've been doing. So we're not too surprised that something in a differential equations class is going to be producing things of that form. Alright, now let's take as a next one fs is equal to 9 plus s over 4 minus s squared. Now there are two approaches we could do here. We could break it down in terms of the cosh and the sinh. We'll need to rearrange this slightly in order to make that happen, or we can use partial fractions. It's up to us, really. I'm going to rewrite this to make it match the elements on our table, and then I'll just use that. Partial fractions is a little beyond the energy level that we have after so long a lecture. So we could rewrite this as negative 9 plus s over s squared minus 4, and that would be negative 9 over s squared, s squared minus 4, plus negative s over s squared minus 4. Now looking at the table, the reason why I did that was I wanted it to match the formats that were on it, and the formats would be for the hyperbolic cosine and hyperbolic sine functions. So we can go with we can consider the Laplace transform of the hyperbolic cosine kt is equal to, so here we've got s over s squared minus 4. So here k would be 2 to match that spot, and would have to multiply by so I guess we're comparing it with this one over here. So we'd have to multiply it by negative 1 to match this one. And then the Laplace transform of sinh x, sinh kx, kt I should say. Yeah, start over. Laplace transform sinh kt is equal to k over k squared minus 4, where here we'll be talking about k equals 2 again, and we'll have to multiply by, well, we're supposed to have a 2 on the top. We instead have a 9, a negative 9, so we'll have to multiply by negative 2, or by negative 9 over 2 in order to get what we want. Okay. So then what we've got here is the inverse Laplace transform of 9 plus s over 4 minus s squared will be equal to negative cosh 2t, and then minus 9/2 sinh 2t. Now here, when we do this, it would automatically produce a factor of k on top, and then we need it to cancel, so that's why it has to be like this. And then, as our last one, let's take something along these lines. So as the last one here, example f of this, let's take f of s to be 2s to the negative 1 e to the negative 3s. Alright, well, when we look at this, we don't see any s's anywhere besides denominators, so we might as well rewrite this as 2 e to the negative 3s all over s, and then try to compare that with anything that matches the format here. Well, it does match the format here on this one. So we've got the shifted unit step function. So the Laplace transform of u sub a, the Heaviside function, at t is equal to e to the negative a s over s. So here, a equals 3 and multiply by an additional factor of 2. So then what that gives us is that the inverse Laplace transform of 2s to the negative 1 e to the negative 3s is equal to u sub a of t times 2. Oops, times u sub 3. Is equal to 2 times u sub 3 of t. So it's the unit step function shifted over by 3 units. Okay, well, that's gonna have to do it. So, join me next episode for more Math 256. I'll see you then. Bye.